The sinusoid itself does not get bigger or smaller in amplitude. Remains always the same. So back to this thing, if we think about something like a signal here that did something like that, what would we think of in terms of the poles? Two on the j omega as complex conjugate pair. That provides the sinusoid. What about the decaying exponential? It's decaying to 0, even though my drawings don't seem to converge there. Like that, okay? Good. So what about on the z-plane? Let's put the unit circle back up there. And by the way, if you look at the way this is done, there's a unit circle and a dotted line on each one of these. So you have that as a reference. Because if I didn't, I could never figure out where your poles were. So it's for my grading purposes more than it is for you. So, the sinusoidal, what would they be? Two on the circle, but we need to figure out where. So you count cycles, samples per cycle. If I start here essentially on the 0, that's 1, 2, 3, 4, 5, 6, 7, 8. Before you get back to the 0, you don't count the next one that's on the 0. Believe me, we're very unlikely to give you an odd number because it's too hard to figure out from the other stuff. I guess it wouldn't be that bad, but do I get 8 here? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8. I drew it right. So where are they? Yep. And so we have 2 poles here. And then one more pole for the exponential. Where is that going to be? Where is this one going to be on the z-plane?
Cheating in just a little bit on.
Yeah, like that. Now, you can figure out exactly where it's got to be if you know how many of these it takes, you know, how much different they each are. But in most cases, if it's just a simple drawing like this, you have to be somewhat reasonable about it. All right, yes?
8 parts C and D.
I have a quick question on that, just really
Let's
quick.
do that first.
So if that sine wave was decreasing in size,
So it was decaying. It's 2 possibilities. It could be a linear, no, not a linear decay, not possible. So if it's a exponential decay, what would be different?
so the ones on the 45,
Uh-huh.
those on the 45, would those be on the inside of the circle?
Yeah, they'd be slightly inside the circle, depending on how fast it was decaying. Yeah.
Okay.
Yeah.
That answers my question. Sorry.
And if it was expanding, getting bigger,
What was that?
if that was an exponential expansion,
It would just be like that one, and it would be outside of the circle.
okay. What if it was a linear expansion?
Wouldn't it be on the axis?
But what would be different?
Outside of it, right?
Not outside, if it's a linear expansion. Double pole. Yeah, each of the complex ones would be double.
Linear expansion, you mean like where it's
Yeah, so the amplitude of this sine wave is growing bigger and bigger and bigger, linearly. The amplitude is growing linear. And it's a bad choice to do that on because it would be easier to do that here. See, this is a exponentially expanding sinusoid, so it's slightly outside the circle. But if this expansion were linear rather than exponential, would they still be outside? What would they be instead?
dead on.
Dead on and double. Yeah, double each. So see how I'm asking you questions like this, and they could come, essentially, you have to know what you were doing on the S-plane too. Good possibility of something like that. Other question, you had one, Steve.
Spring 17, number 8, parts C and D.
Spring 17, problem 8.
Part C and D.
Probably gonna do all of it, I think.
No.
When I see it, I'll
Well, the first part's like find gain margin, delay margin.
Yeah, we should do that anyways.
That's
so you said 8, right?
8, yeah, C and D.
And by the way, look at the next problem on that test. And you were supposed to match it. Unfortunately, I was supposed to get this on this side of the table and the ones you match on the other side of the table.
But it went
Like
the other
this.
way.
So it was really unhandy. So when I noticed that, I actually ran down to the copy center in this building and made a bunch of copies of this page and handed them out to people so they could actually look at it at the same time as they looked at this side. Because it turned out to be extremely unhandy to go back and forth. But the same sort of idea. So that consideration of where the signals are, where the poles are, that's kind of a big deal. And it goes back to the first stuff in the class too. All right, so he is saying, yes, it is different. It doesn't matter about parts C and D if you know the other parts. It's unfortunately very difficult for me to draw. So if there's any way you can pick this problem up and see it, it would help. Spring 17, problem 8, part C. Says, now you've got some plots there. You've got some Bode plots. And you've already done some work to figure out the gain margin and the phase margin. You've got a magnitude plot and you've got a phase plot. Let me see if I can do this halfway decent. Like this, and it basically levels out around 270 degrees. Negative 270 degrees. All right. Now, they're not in scale with one another. I'm sorry, I did my best. But I'm not that good at that. Especially without scales to do it. If I had scales, I'd really screw up. So, part C says, give the steady state response of the open loop system. An open loop system to x of t is equal to 4 sine 30t. This, by the way, is omega in this direction. So, what are we going to do? See if I can figure this. This is about 10 cubed, or about 1,000. Let's see if I can. 1, yeah, about 1, 10. Nope, that doesn't work. 10, 100, something like that. Okay. Yeah, right. Too far off. So what am I looking for here in order to figure out the open loop response, which is this system by itself, the way it is now? What do I need to find from these plots? Because these plots are the magnitude of this plant's transfer function, and it's actually this and the phase angle.
So would you just take the magnitude of top
Yeah.
one and the phase the bottom?
At what frequency?
30.
30. So we find 30 here, and we go up here, and we figure out what that is.
That's an omega.
And omega is a 30, and it's in an omega. So I didn't trick you anything there, at least not on this test. And I get around 7 dB, roughly 7 dB. Is that what I use down here? Yep, it is. And the angle, I look at this right here, the same exact frequency, and I end up, when I look at this, I get an angle of about negative 60 degrees. So what is the Planck's transfer function P of J30 equal to? Because that's what I just read.
7 dB is the phase angle.
Only is the 7 dB in a form that I can use it?
No,
No,
2.24.
So what do I do with the 7 dB?
7 divided by 20.
like that. When I do that math, I come up with 2.24. So I want this as 2.24 at an angle of negative 60 degrees. So the point to this question is, do you understand what the Bode plot is showing you? To the point where you can use it to figure something out. So if we have this at 30, what is this in phasor form?
That's
4.
Oh,
It's 0 degrees. -90. Oh, yep, you're right.
negative 90 degrees like
That's
that.
why.
And why is it negative 90?
the sign.
Because it's
It's
a
a
sine,
sine,
so there's one
vertical
little
sine.
extra thing thrown in there you had to think about. So what we have now is we simply multiply these two together. So 4 at negative 90 times 2.24 at negative 60 gives you what? 2.24 times 4 would be 8, about 9, just under 9, 8 point something. 8.8, 8.9 something, 8.96 at an angle of negative 150 degrees, which translates in the time domain to the output of this system would be what? 8.96. Cosine 30t minus 150 degrees. This is probably the only answer I gave you on the results, right? I gave you the sign as well? Yeah. The other possible answer is 8.96 sine 30t what? Minus 60 degrees.
Arn, I have a question. How did you calculate your negative 60 degrees there?
I just found it on the graph. I didn't calculate it at all. There's no calculation at all. You go up the 30 line here until it crosses. I picked a point where there was a crossing, it was clean. Went over here and got 60 degrees. So there was no calculation involved at all. It was taking data from the graph.
I have a silly question. The 10 raised to the 7 over 20, is it always going to be over 20?
Yes, because when you take the dB, when you get something in terms of dB, you would take the 20 times the log
Oh, yeah,
base 10 of the magnitude of P of, well, I guess J omega.
Okay.
So all we're doing is inverting this
Yeah.
process. And the 20 comes from right there.
Okay.
And why is it 20? Anybody remember?
Because it's old silver volts squared or whatever, squared.
Yeah.
Squared.
Because it really should be in terms of power.
Yeah.
And the
Power's like
relationship
10.
of power to something like volts, in which we're normally working with, there are things that we're normally working with in our transfer functions, is a squared relationship. That's why there's a 2. But why is there a 10? Because it's decimals and not bells. Yeah. If it was in bells, it would be 2 times the log base 10 of V out over Vn, for instance. If it was P out over Pn, there wouldn't even be a 2. You just take the log base 10 of it. Yes, Steve.
So for the part D, would you just do PJ, P of?
Let's see, let me read part D. D is give the steady state response of the closed loop system to the same input. So, do we have to take more data from the graphs, or have we already got it? The only difference is for the closed loop system, we have a new transfer function, which is 2.24 angle negative 60 divided by 1 plus 2.24 angle negative 60. So where does this come from? Now, there is an assumption that it's a unity feedback, negative feedback system, right?
Yeah.
But it's just G of S or P of S over 1 plus P of S. That's all there is to it.